So now let's continue and let's try to get the connection between the accelerations of the two dots of the solid body. So again, let's remember we had the solid body. Here was the dot A and dot B. We got a connection between their velocities. So we said that V1 plus omega R3 is O of VB. R3 is that vector. And now, yeah, we have to get the connection between the accelerations of the two dots. And in order to get it, we have to find derivation for both of the functions that we have here. So we have just to derive this equation. We find derivation for that function. We'll have the acceleration of these dots. Here, let's try to understand what will happen. Here in the vector multiplication, we see that this is and this thing are both functions of time, because we know that in different periods of time the rotation may happen in very different ways. The omega vector can be changed. Consequently, if we find the derivation for that, we have to write that this is the same as if we write epsilon r3 plus epsilon omega r dr3 to the t, and this all will be equal to the acceleration of our b dot. Where is this thing? This is in fact the tangential component of acceleration of that dot relatively to that one. So we can write this tangential component, and let's try to understand what this component is. Omega dr to the t. When we were trying to get the formula of Euler, we got this thing, the derivative of the vector r3 is omega r3. So using this result, we can write here that this component of acceleration here is the same as this one. So let's try to remember the rules of vector algebra, and then we will have that this vector multiplication is equal to where we'll see now. So this is omega r3 minus r3 omega squared. But consequently, these two vectors that I've written here are perpendicular to each other. We see it from this very formula. And if it's so, and then it means that we can get rid of it. And this thing then, we see will be equal to this one. And where it is, in fact, this is the normal component of acceleration. Normal component of acceleration of B relatively to A. So the result we'll have is that the acceleration of the B dot is the sum of three components. The acceleration of A dot plus A tangential and A normal. So this is the result we've got, and this thing is also called Rival's formula. Okay, the next thing we have to study about the solid bodies is the thing that is called the is the fact that the angular velocity of any dots relatively to any other dot of solid body is the invariance thing, invariant value. And now let's try to get this and to prove, and we will try to understand what it means, of course. So imagine we have such a solid body. Let's try to choose three different dots that won't lie on one line, and then what we'll do, we'll write the formula of Euler for that dot relatively to dot A using the dot A. So we'll try to find the connection between the A and B dots using Euler formula. So we'll write that VB is VA plus the vector AB, omega AB, sorry, omega AB. Okay, then the next thing we'll do is we'll write the same formula. We'll try to find the connection between the velocity of the c dot and a dot. So we can write that vc is va plus omega ac. You may have the question why omega here and here are the same, but in fact it's connected to the fact that I'm trying to find the connection of velocities of the two bodies with this one, with this very dot, and how they rotate relatively to the dot A is the same. Is similar thing. The angular velocity for both of them relatively to A dot is the same. Okay, the next thing we'll do is that we will try to write the velocity of this dot using the vector, the knowledge that we know, for example, the velocity of vector b. So we will write that vc is vb plus omega 1 bc. And here I have written another vector omega 1 because I can't say that omega 1 and omega are the same vectors without proof. So I have to prove it somehow. Now, using this system of equations I've written, let's do something. So let's write that Vc on one hand is equal to Vb plus omega 1 Bc. And we know it from the first equation, but on the other hand it's equal to what we've written in the second equation. So this is Va plus omega Ac vector. But we also know that the vector Vb is connected with the velocity of the A dot in that very way that I've written in the first equation. So let's use this first equation and rewrite this equation using this connection. So then we'll have something like that. We'll see in the equation that we've got, we see that we can get rid of this component then, and we can rewrite this equation that we've got using the vector algebra rules in that very way. So omega AB minus AC, that's equal to omega 1 vector BC. And we have now to write another fourth equation. It will give us the connection between the radius vectors that shows us the positions of each of the dots relative to each other. So we can draw such a picture, and we have that AB vector plus BC vector is equal to AC vector. And using this information and using this equation, we may get very obviously we can get that omega vector is equal to omega 1 vector. So this is the result I've said to you about what we had to prove. It means if I try to study the motion of the dots of the solid body relatively to one of the dots, the angular velocity of that dot relatively to A will be the same if I try to study the motion of all of that dots relatively to the B dot. So again, the vector of angular velocity relatively to A of any of the dots of our solid body will be the same as the vector of angular velocity relatively to the dots B if we study the motion of the dots of the solid body relatively to it. So this is the result we've got, and it's quite interesting result that sometimes we may use when we solve different kinds of problems, especially concern this topic.